So we had a Google Sheets and GeoGebra submission due this morning, and I sent you a Canvas message. Well, I sent a couple messages to you on Friday and a message to you this morning. And from what I've kind of skimmed over, I haven't graded any of them yet, but they look to be pretty good. But of course, like if I have a submission due Monday morning, Sunday night starting about 8 o'clock, 9 o'clock, 10 o'clock, 11 o'clock, the emails start to come in, and there are bumps along the way with this process. Obviously, the environment that we're learning in, GeoGebra, we saw a couple hiccups with it last week. One of my messages last week was I think I found a solution to get GeoGebra to work, okay? I had been linking you to a version that wasn't targeted for the Chromebook. My mistake, I should have vetted that out a little bit better. But the current link from my Canvas homepage is a version that seems to be working appropriately for the Chromebook. It's been updated like within the last week as opposed to the one before. The last update was like in 2018, so I've tried it on my Chromebook and I think everything's working much better now. So if you don't have that Chromebook version, try following that link and installing that. I think that will work through a lot of the problems that we saw with like not being able to click on the gear or able to get the descriptive statistics up, okay? With that being said, I've decided to postpone the submission deadline by 24 hours. So tomorrow morning by the end of homeroom, if you have not submitted anything, which didn't look like many people just yet, if you did not submit anything, then yeah, you're able to do that and get it all done for tomorrow. You will not have any new assignments for today. If you kind of like hastily threw something together to get it submitted on time, but with a little bit more time and like a work day and like built-in study periods in the school day, if you feel like you can like polish that up a little bit and resubmit or get questions answered either from me or from your classmates or just by trying it again, you're welcome to do that and resubmit, because the purpose of this assignment is to familiarize ourselves with GeoGebra. We're going to be using it, well, today, again, in a different aspect, but we'll be using it throughout the year. It's not so much that I care about like perfect stem plots or box and whisker plots or anything like that. It's like I want you to have a good understanding of how it works so that like later on in the year we can just, all right, go to GeoGebra and calculate this, as opposed to like, how do I get this to do this and everything. So it's a guide, it's a walkthrough. Hopefully I can like easily score most of these 15 out of 15 when I go through those, okay? Any questions on that? Anybody at home with your icons shining here? No? Okay. So what we're doing today, let's take a quick look at the Canvas agenda for this week. This link will be our video from our class today. But we have our lesson link right there. This table of z-scores we'll be bringing up a little bit later on in class today. We should be able to get through the full lesson today. When I see you on Wednesday, we're going to be, the homework for this chapter is a little bit different. We have a couple of smaller calculation-based assignments that we'll be going through a few examples together on Wednesday, and then you'll finish that on Wednesday, due Thursday. Okay? When I see you Thursday, we'll practice those same types of calculations, but in like a word problem type context, a real world context. All right? So I think there's like 5 additional problems that will be due Monday, and then next week, we have our book assignment, which is a little bit of everything. That's kind of in the background. I have it starting right here, but that is not due, the book assignment not due until the following Wednesday. Okay, so you got some time with that. You can kind of chip away at that, or you can put your focus on that assignment after we get through these two assignments. But all in all, we are starting to look at a quiz probably the end of next week. Okay, so probably Thursday of next week will be our first quiz, and we'll prepare accordingly for that. Okay, talk about format, all that stuff. All right, all of these due dates and assignments, they are on Canvas calendar, so use that to help you. Also be thinking about that September 30th date is the last day for applying for the PIT credit too. Okay, so I think across all of my sections, I think 6 people have signed up for the PIT credit, but I know that usually waits until the last minute, but again, PIT is very steadfast in their deadlines. Okay, there's nothing I can do if you miss a deadline. Okay, so just be thinking about that. All right. Any questions on our housekeeping issues? Okay, going back to Squid here. Today we are talking about the normal distribution, and they actually have it plural, normal distributions, and we'll see what that means. I usually think of it as singular, but what do I know? Our targets for today, looking at some key features of density curves in general, but specifically normal distributions. These population proportions with the empirical rule, okay, 68, 95, 98, 99.7. Kind of a quick and easy way to get a general idea about some data sets. And then using a table, but probably technology to assist us with calculating percentages, population proportions, or percentiles, whatever you want to call them. Also starting with a percentile and going back to get a raw data answer. Okay? We'll have a better understanding about what all this means by the end of class. Okay? I know that some of you are approaching this topic with a little bit of background. Okay, FST, you may have done a little bit of work with the normal distribution and z-score calculations. If you have, that's great, and hopefully we can build on to that with our work today. If this is brand new for you, that's okay too. I want us to have the background perspective to make sense of all of this. Now, in general, a density curve. Okay, it says we now have a toolbox of graphical and numerical methods for describing distributions, right? Okay, we learned about all these different displays of data when they're appropriate, okay, whether it's categorical data or quantitative data. We also have these statistical calculations, numerical methods for describing a set. Okay, we have the descriptive statistics, whether that's mean and standard deviation, or if we're looking at a set of data that has like extreme values, possible outliers, okay, using the 5-number summary and the median to describe that data set. Okay, so this is what we've done so far, these 3 steps. Plot your data, make a graph, okay, look for an overall pattern, the shape, the center, the variability, okay, any striking deviations as possible outliers. Calculate a numerical summary to briefly describe the center and the variability. Okay? Now, our new step for today says sometimes the overall pattern of a large number of observations is so regular we can describe it by a smooth curve. Okay? And when this happens, there's a whole bunch of other analytical tools that we can use to help us understand what's going on. In general, what we are doing is we are transitioning from talking about pictures and shapes of a set of data, okay? Basically a sample is what we've been talking about, like stuff for the class. And we're transitioning into talking about pictures and shapes for populations of measurements. Okay? Could we use what we observed in our class sample to describe what's going on for high school seniors across the building or high school seniors across the country? Okay? We're going from talking about a sample to a population as a whole. Now, we've been working with a histogram. Okay? This particular example is a histogram for vocabulary scores of 947 seventh graders. Okay? So you've heard coming up through school, like this student reads at a second grade level. This student reads at an eighth grade level. Yeah? Well, in seventh grade, you would expect a student to read at a seventh grade level. So that is located right at the center of this curve, right around here. Now, you can see that it's a pretty normally distributed model. Okay? Most of the students are reading at 5th, 6th, 7th, 8th, 9th grade level. Fortunately, very few students reading at a very low level, and we have very few students that are very far advanced, reading at like an 11th grade level in 7th grade. Okay? Most students are right around the middle. Now, this is what we saw across a pretty good sample, almost 1,000 seventh graders. But if we were to use this to talk about the population of all seventh graders, think about what would happen with this. Okay? This histogram would be smoothed out and become this curve. When we're talking about the population as a whole, that's what we mean when we're talking about a density curve. Yeah? Now, you'll see some similarities if you're taking calculus simultaneously. You're also talking about area under the curve as a branch of calculus. And one of the methods for approximating area under the curve is essentially building histograms under it and calculating all of these bar areas, these rectangular areas. Now, the area of these rectangles, these bars, if we wanted to know what proportion of the scores observed were less than or equal to 6, so what percentage of the students in 7th grade read at a 6th grade reading level or below? Well, you're taking the area of this bar, this bar, this bar, this bar, all the way down and dividing it out of the whole. We get a proportion equal 0.303, or about 30% of the students read at a 6th grade level or below. Now, this curve representing the entire population, okay, if we were to calculate the area under this curve at 6 or below, we don't know how to do that just yet, but we get an area there of 0.293, okay? Very close to our sample approximation. They're off by like 1 percentage point, 29.3% compared to 30.3%. And what would happen as that sample size got larger and larger, you'd have more and more data to fill in this, and you could get more and more precise with your histogram. Okay? This would get smoothed out, and eventually this histogram would become this curve. Big picture, that's what's happening with a density curve. Okay? Now, a couple of general rules here. Density curve, it's always above the horizontal x-axis. Okay? Some of those calculus examples, if you're taking it, it would dip below the x-axis. Like think about the graph of a sine function. Okay? It's above and then it goes below. And the way you treat that in calculus is, well, I've got this curve above and this curve below. They balance each other out and they go to 0. Okay? Here we're just concerned about the positive. Any density curve, the area under that curve is exactly 1, okay? Which explains why we treated those as decimals there, but you can think of them as percents. Okay? You can think of it as 100% of the population is under that curve, and that 0.303 is thought of as 30.3%. Now, density curve describes the overall pattern of a distribution. Area under the curve and above any range of values on the horizontal axis is the proportion. Okay? Now, no set of real data is exactly described by a density curve. Okay? This is envisioning the population as a whole. Okay? There's always variability. Okay? So this is compared to what theoretically should happen across the big picture. We described a little bit of this last week when looking closely at mean and median. Okay? We know the median is the middle number, and in a perfectly symmetric curve, they are the same value, right there in the center. But if it's not perfectly symmetric, the mean is pulled in the direction of extreme values. So here we have a data set that is skewed to the right. The mean is pulled in the direction of those extreme values. Okay? You can think of the mean as the balancing point. Like if this were a solid object, if you were to like go down to like shop class and cut this out, okay? The mean is thought of as the balancing point. That's where that figure would balance, because even if you have extreme values way out there and most of the data down here, okay, well, that extreme value gives you a little bit of torque there. It's balancing it out at the mean. As opposed to the median, it's that middle number, okay? So it's steadfast in where it's falling with respect to 50% below, 50% above. But it's the mean that might need to go out on that limb to keep that data set balanced. Okay? That's all if it helps you to visualize what's going on here. Okay? I'm not going to have a test question like, is it the mean or the median that's the balancing point of the density curve? No. We are concentrating on this, where we have a symmetric data set. We've talked a little bit about notation already. This is just a reminder that when we're referring to the sample, okay, actual observations, the mean is x bar and the standard deviation is lowercase s. When we're talking about the entire distribution or the population, the mean is the Greek letter mu, and the standard deviation is lowercase sigma. Okay? So today, as we lay out the density curve and the population, we're going to be using these symbols. Compared to last week, we were mostly using those symbols. Again, this is mu and mu. This is sigma, okay? Lowercase sigma as opposed to capital sigma that you might be more familiar seeing, that Greek letter. Now, I had said that you could think of normal distributions, plural, because you have different shapes depending on the size of the standard deviation. Okay. We are using two numbers to describe any normal distribution: the mean and the standard deviation. Now, mean is always at the center of the curve. Okay, it's perfectly in the middle. And it also is the median, and it also is the mode. Okay, remember, height of this is the frequency. So the most commonly occurring value is at that peak. Well, that's the mean. Okay, but it's also the mode. Now, the standard deviation dictates how wide and spread out this data set is, but that also, in turn, dictates how tall this distribution is, right? Because if you have, let's say, a whole wide variety, let's say that we take a test and the average test score is 80, but pretty much everybody scores between 75 and 85, then we have a distribution that's kind of like this. There's not much variation in the data set, so the standard deviation is pretty small, and this gets taller because the area under both of these curves is 100%, but in this case, everybody's jam-packed around the mean, so standard deviation is small, and the height of that curve is very tall. As opposed to, we still have a mean of 80, but now we got some people scoring like 40, 50. We have some people scoring 95, 100%. I still, whatever those values are, still make it normally distributed, but there's a whole lot more variability in that case. So the standard deviation is wider, which flattens out this distribution because now the values are more spread out. Okay? But most of them are still around the mean. It's just there's a wider spread around the mean now. I already talked about most of this. Changing mu without changing sigma moves the normal curve along the horizontal axis. So let's say here is my previous class's test scores distributed like that, and then you guys come along and you guys do better, but still in a normal distribution, and your distribution kind of looks like that. Okay? The mean is different, but the standard deviation we'll say is the same. Okay? You just translate that along the x-axis. Or maybe it's a little bit different and there is much less variability because you guys scored higher and 100% is the maximum. Now I have people scoring up here and there's not much variation there and not many low scores because you guys are overachievers. Okay? This is a very tall point right here, okay? And it's wider, but it's still symmetric data set. Okay? It's the standard deviation that controls the variability of a normal curve. When standard deviation is larger, the area under the normal curve is less concentrated about the mean. It's more flat and more spread out. Normal distribution is a normal density curve, specified by the mean and standard deviation. We already said that. Now, when we say that a distribution is normal, okay, normal, standard, bell, symmetric, those are all words that we use to describe this. But when we say normal, one of the reasons we use that word is because it occurs so commonly. A normal distribution is common. Okay? We talked about some of these last week, but physical measurements within a homogeneous population, they fit a normal distribution. If we were to look at the average adult male height, I think is about 5'10". Well, there is a standard deviation that goes with that. I think it's 3.5 inches or something like that, 3.5 or 4 inches. Okay? So 5'10", 3 inches above, we'll say, takes you to 6'1", another 3 inches takes you to 6'4". On the lower end, 5'10", down to 5'7" would be 1 standard deviation below, 5'4" would be 2 standard deviations below. Okay? So me, an adult male who's 6'2", I am like 1 1/3 standard deviations above the mean. But I'm around most of the population of adult males. We have very few individuals who are extremely tall, very few who are extremely short. Most of the population is somewhere near the center, if not at the center. Standardized tests. Okay? PSSAs, Keystones, SATs, ACTs, they are all standardized against the population to allow for comparison of individuals. So SAT this fluctuates every year, but the mean for a section of the SAT is usually about 500 with a standard deviation of about 110. Okay? So this gives you some perspective in comparison to the mean. Okay? Here it is laid out. If I've got 500 right there at the center, one standard deviation above would be 610, two standard deviations above would be 720, and so forth. Okay. And we can get percentages that allow us for an even better comparison of our value to the rest of the population. Now, one last example of the pervasiveness of a normal distribution that I want to talk about is an IQ score. Okay? IQ stands for intelligence quotient. And I listened to like a podcast about IQ and intelligence in the spring. And like I've used this example in class before, but I never really knew like the shady roots of intelligence and measuring intelligence before. Like it's actually a very if you're into history and stuff like that, it's pretty interesting, but it's a human-made creation, right? Like some of these measures humans have created as a way to define and compare individuals to each other. Intelligence is supposed to be something that is set for age, or I'm sorry, is set for life. That really, like once you get past the age of like 6 or 8 or something like that, that your intelligence is pretty much set, like pending like a major traumatic brain injury or something like that. But it's pretty much set so that like, nothing can do, you can't study, it's not a test of trivia or anything like that. An intelligence test is supposed to be independent of both age and language. So an 8-year-old English-speaking student should be able to take pretty much the same IQ test as a 60-year-old French-speaking person, because it's about pattern recognition, it's about like shapes and what you see and things like that. There might be some directions and a little bit of language that's translated to the language that the person speaks, but it's pretty much the same. Now, intelligence, okay, there are a few different IQ tests, but an IQ test is typically thought of as having a mean of 100 and a standard deviation, this Stanford-Binet is the standard, of 16. Yeah. Now, IQ scores have been used for a lot of things. I think as a society, we're kind of getting away from using IQ, at least in an academic setting, because it has some things that aren't so ideal about it. And it used to be used for comparing individuals and discrimination against those individuals back in the 20s and 30s and things like that. These are historical classifications that were used based off of IQ, and just for like a snapshot in history, like think about what this was. Like these were actual medical classifications based off of IQ. Okay, on the upper end we had very superior, an IQ score of 128 and above, and then going down, superior, bright normal, average, dull normal, borderline, defective is 65 or below. And that was further subcategorized as a borderline deficiency, a moron, an imbecile, or an IQ below 20 was an idiot. Now think about that. Like these are classifications in the 30s and the 40s and the 50s. Okay? And it was around longer than you would like to think. I don't know when they were completely changed, but now scores like that, okay, they're referred to as mild, moderate, severe or profound impairments, okay, as opposed to some of these other classifications. But it's kind of interesting to look at like where we were as a society, and this is like the medical community here. Like, they are pretty educated, but not very sensitive in terms of the labelings that were used at the time. But IQ is kind of like a textbook example of a normal curve, where most individuals are somewhere around the mean. Okay? Very few individuals that are extremely low, very few individuals that are extremely high. Okay? Has anybody heard of the group Mensa? Let me write it out here. Mensa is an organization that I think you need an IQ of like 140 or above to be a member of. It's a group that they do solve problems together or whatever. They kind of use that as their threshold for entry into their organization. Albert Einstein, I used to remember what his IQ was tested at. It's like I want to say like 190 or something, which you can see is very high up on this scale. Okay, I know there are people who have tested in the 200s for IQ, which would be extremely unlikely based off of this distribution. Okay? But we see an IQ example from time to time, and I wanted to give you a little bit of background perspective about the roots of that and what it looks like. Okay. So moving into this 68, 95, 99.7 rule, or you'll sometimes see it referred to as the empirical rule. The empirical rule is a quick way for us to identify how a value relates to the rest of the population. Okay? What this says is that we have our mean right there at the center of the distribution. Within one standard deviation, so one standard deviation to the left, one standard deviation to the right, we have 68% of our data, 68% of the population. So that's about 2/3. Okay? So we're talking about the heights of adult males. And if the adult male mean is 5'10" and a standard deviation of 3 inches, we are saying that 2/3 of all adult males are between 5'7" and 6'1", okay? Which is pretty good. I mean, it's clear majority. Okay? 2 out of every 3 people. If we were to expand that even further, so 2 standard deviations to the left, 2 standard deviations to the right, we have 95% of the observations. 95% is a pretty good balance of a pretty high level of certainty, right? 95% is 19 out of 20 people would be within that margin. We're going to be using this level of confidence quite a bit throughout the year. Okay? It's only 5% uncertainty. Lastly, 3 standard deviations. And 3 to the left, 3 to the right. We have almost 100%. 99.7% of the individuals would be within 3 standard deviations of the mean. Now, that seems pretty good, and it is, right? Change the scale of this, you're saying 997 out of 1,000 people would fit in that range of values. So that's almost as close as you can get to with certainty. The problem with that in terms of like predictability is that you're saying 3 standard deviations to the left, 3 standard deviations to the right. That's an extremely wide margin. Okay, so it's not that descriptive in terms of trying to predict, like, well, I'm 99.7% certain that it's going to be between this value and this value, well, that doesn't really help at all. As opposed to, I'm 68% certain that it's between this and this. Okay? That's a much more narrow margin, but maybe 68% isn't high enough confidence. Okay? So that's why a lot of times we'll see that 95%, 2 standard deviations to the left and the right, that's a good compromise. It's a good balance of the two. Okay? We'll revisit that later in the year. Now, here's an example that we can explore with this empirical rule. We have the distribution of Iowa Test of Basic Skills vocabulary scores. So this would be like the PSSA for Iowa. Okay? For 7th grade students in Gary, Indiana, why are the Indiana students taking an Iowa test? I don't know. It just occurred to me. Get those I states, those Midwestern I states confused. Anyway, let's ignore that. The distribution is pretty close to normal. Now, if you see data presented like this, okay, normal, this number, comma, this number, that means mean, comma, standard deviation. Okay? So we have a mean score for this set of 6.84, standard deviation of 1.55. So it says to sketch this density curve out, and that's what's done down below here. We have the mean of 6.84. I'm going to go to this next slide where this graph is bigger. And we have a standard deviation, 6.84, standard deviation of 1.55. Okay? That is our step size, right? So I add on 1.55 to get to 8.39, to get to 9.94, to get to 11.49. Same thing's going on to the left. Subtract 1.55, 5.29, 3.74, 2.19. Okay? Standard deviation acts as the step size when you're looking at the graph like this. Now, with these values labeled out, we can answer some of these questions here that says, like, what percent of the vocabulary scores are between 3.74 and 9.94? Well, conveniently enough, these numbers look familiar, 3.74 and 9.94. Those boundaries, 2 standard deviations to the left and 2 standard deviations to the right. And from our empirical rule, we know that 95% of the values will fall within 2 standard deviations. So we have 95% of the students scoring between 3.74 and 9.94. That was a pretty straightforward example, right? Okay, those are just labeled out there on the bottom. Now, our next question here, what percent of the students scored above 5.29? This approach is a little different here. 5.29 is right here. We are interested in the students that score 5.29 and above, all the way up. That empirical rule is laid out going away from the middle, right? Within 1, 2, 3 standard deviations of the mean. Well, this 5.29 is 1 standard deviation left of the mean. And we do know that within 1 standard deviation left and right, we have 68% of the data. But the important thing to remember about a normal distribution is that it is symmetric. It's a mirror image, left and right. Yeah, remember, that mean is also the median, 50% below, 50% above. So that 68% can also be split into 34% there, 34% there between the mean and below, or the mean and above by 1 standard deviation. So I have this 34% chunk that takes care of this, but I also want all the rest of the way up, which we said is an additional 50% going all the way up. So I add those two together, and I have about 84% of the students scoring above 5.29 on this test. Any questions on what happened there? I could also flip that around, get the complementary score, okay, because everything under this curve is 100% of what's happening. So if I've got 84% going on above this, 100 minus 84, I've got 16% performing below that value. I could additionally kind of carry it out further, like we had said that within 2 standard deviations we have 95% of the data. So 100 minus 95, that leaves us with 5% left for the 2 tails. And again, it's a symmetric data set, so that means we've got 2.5% below 3.74 in this tail, and another 2.5% at 9.4 and above in this tail. Okay? So the empirical rule is a way to kind of slice it up and in conjunction with the idea that it's symmetric and 50% above, 50% below the mean. You could figure out what's going on in each of these slots. You could figure out what's going on from here and up or here and down. Okay? You can do a lot with just that if you have an integer number of standard deviations above or below the mean. Okay? Now, it doesn't always work out that nicely in a perfect number of standard deviations above or below. That's where we get into z-scores or standard scores. Okay? Normal scores, z-scores, standard scores, they are all the same thing. Now, what this does is it allows you to compare your value in relation to the mean and in relation to the rest of the population that's being modeled. Okay? We use this equation to help make that comparison. Okay? A z-score is calculated by taking your value x minus the population's mean divided by the population's standard deviation. This will give you a z-score. Now, let me say it now because I know this question will come up. A z-score, or standardized score, or normal score, is the number of standard deviations above or below the mean. A z-score is the number of standard deviations above or below the mean. Okay? So if I took that IQ test we were talking about before, and it had a mean of 100, write this out here. The mean was 100 and the standard deviation was 16. Let's say my IQ was 116, right? I'm above the mean. I could use this equation. 116 is my value, x, minus the mean of 100 divided by the standard deviation of 16. Now, careful order of operations, parentheses are not drawn in there, but you know this is done first. 116 minus 100 is 16. 16 over 16 is 1. I have a z-score of 1, which means I am 1 standard deviation above the mean. Okay? In this case, because it is an integer value, I could use the empirical rule to place myself with respect to the population as a whole. Remember, within 1 standard deviation, 68%. Split that in half, I'm 34% above the mean, and the bottom 50% is there as well, so my IQ, if I'm 116, I have an IQ higher than 84% of the population. 16% of the population is still above me. A couple other examples right here. The heights of women aged 20 to 29 in the United States are approximately normal. a mean of 64.2 inches, standard deviation of 2.8 inches. Standardized height is found by doing your value minus mean divided by standard deviation. So let's say a woman is 70 inches tall. Okay, 70 minus that 64.2. So we're looking at what, 5.8 divided by 2.8. She has a z-score of 2.07, which means she is 2.07 standard deviations above the mean. Similarly, a woman who is 5 feet tall or 60 inches, okay, 60 is below that mean. So look what happens with that subtraction. We're going to get a negative number. That's okay. A negative z-score just means you're below the mean. Okay, you are 1.5 standard deviations below the mean in this case. Now, I've talked about plural standard normal distributions. Okay. This refers to the standard normal distribution, is kind of like a theoretical mathematical concept from which everything else is a translation or transformation of. All that's saying is that you have a mean of 0 and a standard deviation of 1. That is the normal distribution. You don't really need to worry about that. We're not into the theory here. We want to use it in practice. This is important. Cumulative proportions. Ideally, we would like to be able to relate our value to the rest of the population. Okay? This is a percentile, okay, or a cumulative proportion. I talked about how if my IQ was 116, I kind of used the empirical rule to say that 84% of the population was below me, 16% of the population was above me. Okay, a cumulative proportion starts low and adds everything up until your position. Okay, everything that is less than or equal to X. Remember, that was one of our options with our histogram on GeoGebra when we were playing around with the options there, was to turn it into a cumulative proportion. I have an example here that says who qualifies for college sports. The combined scores of almost 1.7 million high school seniors taking the SAT in 2013 were approximately normal with a mean of 1011 and a standard deviation of 216. What percent of high school seniors meet this SAT requirement of a combined score of 810 or better? So we could do our z-score calculation. We have an 810 as our minimum score for being able to play college athletics. And then we are subtracting away the mean, which was 1011. Oops. And divide that by the standard deviation of 216. Okay. The visualization of what's going on here, okay, is taking the area to the right of that point, and we have our total area. Okay? So this area to the right is we're subtracting away the area that's below. Okay? It's really important that we recognize that 100% everything that's possible is the area under that full curve, so that we can add and subtract these pieces away from one another. Now, it gives us these percentages here. In this case, it says that we have 18.73% below this 820. Okay, so 18% of the almost 2 million people taking the SAT score below an 810 combined score. That has 81% of the population scoring above that. Now, these percentages just kind of appear. We need to figure out where they come from. Technology is a good way to help us do that. Okay? And this is where GeoGebra is very helpful, and that's why I wanted us to make sure that we are able to use that effectively. Now, when you first open up GeoGebra, we were using the spreadsheet perspective. Okay? It has a few different perspectives to choose from. Okay? One of them is like the coordinate plane that's there. We're really not going to use that this year. For what we're doing here, we want to select the probability perspective. Okay? So just make note of that. Now, when that happens, a window like this will come up. Okay? And I'm going to have this bigger on our next slide here. This is what it looks like. Okay? We can select the type of distribution that we have. We have a normal distribution, so that's the default. We provide the mean and the standard deviation. Now I realize that the mean they said in the problem was 1011. Here I have 1010, so our decimals don't match perfectly, but you get the idea. Standard deviation was 214. We have these different options down here for where our boundaries occur. Now, the one that I have in this screenshot is both the left and the right, where I want the percent of values that are here or below. So what I did is I said that 820 was my upper boundary, and my left boundary went all the way down to 0. Now, I could have made this easier on myself and selected this option right here, which automatically takes it all the way to the left, and I just provide the upper boundary of 810, and it automatically calculates that for me. 18.73% of the population is there or below. Really easy to use. Okay? I could change this if I wanted the remaining, what do we have here, like 81% that's above. I could have changed that to this option right there, and now that 810 is my lower boundary, and it's going to calculate everything that's above. That would be the complement of this, about the 81%. Or if I wanted something in between, then maybe I wanted something like who scores between 1,000 and 1,400, then I keep it with this middle boundary and I go 1,000 to 1,400. There's my answer. Okay? It's really quite simple to use. Okay? Graphing Calculator does this as well. It's not as easy to use, but I might kind of quickly overview that on Wednesday when we meet virtually. Google Sheets does do it as well, spreadsheets do, but the commands are not necessarily intuitive. It takes a little bit of practice and familiarity with that. Okay? Now, before we had these programs available to calculate these values for us, we did this with the z-score equation that we looked at and a table of z-scores. Okay? One of the things I have linked at the top of our Canvas agenda for this week is this table of z-scores. What this does is, based off of the z-score that we calculate, it allows us to identify what the cumulative proportion is up to that point. Okay? So let's say back here we had let's use my IQ score. Let's say this time I performed below the mean. Let's say that my IQ score came back as 84. Okay. Well, no, let's go a decimal number. So let's go 76. Okay. Let's say that 76 was my IQ score. And z-score calculation, okay, 76 minus 100 divided by the standard deviation of 16. So I can see that I am 4 over 16, and this is a negative number there. And that's a negative sign, then the equal sign. I I am 1.5 standard deviations below the mean. Now, the way this chart works, if I'm below the mean, I'm in this field of decimals. If I'm above the mean, I'm in this field of decimals. Our first column identifies the ones place and the tenths place. These columns going across the top represent the hundredths place. So my z-score is negative 1.50. So I'm going to be on this left side here, and I look up negative 1.5 is right there, and I don't have to go very far. I just want the 0.0 column. So that means that 0.0668% of the population is below me. Everything on this chart is red for what is below. Okay, here and below, whether that's below the mean or above the mean. Okay? These are cumulative proportions or percentiles. Okay? A newborn baby. Okay? Baby's born, the doctor takes the measurements, height, weight, head circumference, stuff like that, and gives an accompanying percentile that goes with each measurement. It allows you, as the new parents, to relate where your baby is with respect to the population of all newborn babies. So let's say that there's a baby who's 4 weeks premature. You might have a weight that is in the 15th percentile, which means that the weight is above 15% of all of the babies that are also premature. Okay, so you compare it to similar populations. 85% on the flip side of that, 85% of the population of 4-week premature babies would be above. Okay? It's a value for the parents. More importantly, it's a value for the doctor to help gauge the level of care that that new baby needs. Okay? It's not everything, but it's a snapshot of something that allows the doctor to have some perspective. And you know, growing up, getting annual physicals or something like that, doctor will still give you, like, your height is in the 80th percentile or whatever. Okay? Well, that's what a percentile is. It's the cumulative proportion up to that point. That percentage is below you, get the complement of that, that percentage is above you. Okay. Questions so far? I haven't been very good about pausing and asking for questions. Now, my recommendation would be to get familiar with GeoGebra. That is a lot easier than this chart of decimals. This will give you a headache just kind of looking at this. Go back here. So that's what they did here. And that's where those numbers they came up with, the 81%, it came from a table of scores. Yeah, you could provide 2 boundaries like that. GeoGebra, that's really easy. As opposed to working with the table, you're doing a lot of math to take like the whole and all the way down. Like if I wanted this red region here, I'm doing this z-score and all the way down, minus this z-score and all the way down, and I'm left with what's in between. Yeah. It's not unbearable, but you can really shortcut that using technology. It's just overviewing how to use the table. Now, last thing for today, we might also have to work backwards. Okay, you're given a percentile or a percentage, and you want to figure out what the raw score is that goes with that percentile. Okay? It says SAT reading scores for a recent year are distributed with this. Remember, mean 504, standard deviation of 111. How high must a student score in order to be in the top 10% of the distribution? Well, sometimes you get information presented like that, like maybe a scholarship is awarded to the top 10%. Okay? So how do you identify what that percentage is, or what score do you need to be in the top 10%? Well, with GeoGebra, what we do is we provide the information we have. Okay? Let me go to this screen again. Still a normal distribution. Mean in this case was 504. Standard deviation was 111. The boundaries here, we want the top 10%. So we have the lower boundary. So we're going to select this box, and we want this to go all the way up to the positive infinity. Now, we want 10% there. So previously, we entered this number and it spit out this answer. Now, we enter it into this box, and it will provide us with this answer, whatever that boundary value is. So remember, we need to speak in terms of decimals. That is the percentage. So top 10%, we're putting 0.1 in there as our decimal, and it will say that a score of 646 on that portion of the SAT would place you in the top 10% with respect to the population. Pretty straightforward to use. Any questions right now? We'll see this in practice a little bit more on Wednesday virtually. Okay, I'll bring up GeoGebra and we'll do a couple of problems together like that. If you're to use the table for this, okay, this is rather painful because now what you're doing, I want to be in the top 10%, and this table is built for what is below. So that would mean that I need 90% of the data to be below me. So I have to hunt down 90%, 0.9000, as close as I can get to that in this field of decimals and work backwards. Okay, so I'm above the mean, so I'm somewhere up here, looking around 0.8989. Okay, so this is where it transitions between 0.89 and 0.90. Okay, this one's a little bit closer to 0.90. So to the left, that's 1.2 going up 0.08. So I have a z-score of 1.28 that would go with my standard score calculation. Switch screens back here. Okay? So 1.28, okay? There it is. Now that's the value that I have to set up in that z-score equation. X minus the mean of 504 divided by the standard deviation of 111, and I'm solving this algebraically for x. Multiply both sides by 111, add 504 to both sides. Here it is. There's that 646 that we saw from GeoGebra pretty easily. Okay. So part of this is me to show you both sides so that you recognize how much easier the technology is as opposed to the chart, doing it by hand. Any questions with this? All right. That's just the step-by-step for this. So I want to end today by talking about kind of like a real-world example of this. This is a case study from the early 1990s, and it's a sad story here, but kind of gives us some perspective. There was a woman who was charged with killing her child, and the headline says, "Jury urges mercy for mother who killed baby." And the defense was an insanity plea, saying that the mother had an IQ lower than 98% of the population. So think about that. Okay, lower than 98% of the population on our normal curve, 98% below. her IQ has 2% of the population below her. Now, you could do this backwards to get what that IQ score was. Okay? So we could hunt down in that field of decimals, okay, 2%, or use technology to assist us with that calculation. Her z-score is negative 2.05, so she is more than 2 standard deviations below the mean, which equates to an IQ of about 67. So the argument is that with an IQ of 67, her defense was saying that she didn't know what she was doing when she took the life of her newborn baby. Now, in this case, in this courtroom setting, this is where you would have probably a psychologist take the stand and interpret what this means for the jury. Talking about 98% of the population has an IQ above her, whether that low IQ is a defense between what's right and what's wrong, that's where the defense attorney has to make the argument about she didn't know what she was doing at that point. But just wanted to give you a little bit of an example of how that kind of comes into play when you're relating an individual to the population as a whole. So, sorry to end class on a bummer like that. Pretty sad story, but does anybody have any questions here? I know I went through a lot of information today. As I overviewed at the beginning of class, on Wednesday, virtually, we are going to walk through and practice some of these calculation examples together and then have you start a few on your own, okay? And you'll have a quick assignment that's you doing these calculations, no greater context, just doing problems like algebra style. Then when I see you next on Thursday, then I have some real world example problems, same types of calculations, but now there's a greater context to it, word problems, and we'll work through those. You'll have a little assignment like that, okay? Kind of building up our skill level, and then early next week, that's when you'll have your book assignment, which kind of covers the whole spectrum. That will be due next Wednesday, okay? Working towards a quiz probably next Thursday. All right. Actually, you guys need to stay put. People at home, any questions? All right. You are free to sign out. Have a good Monday.